Hi everyone. In Unit 8 thus far, we have been looking at aqueous solutions that either have acid or base in them and learning how to calculate pH. It will also be very useful for us to understand, well, what happens if it's just plain water with no acid or base dissolved in there? Well, what we're going to find out is that there is no such thing as a glass of pure water because of autoionization. Let us take a glass of water at 25 degrees C. And what we have are liquid molecules of water, and I'll draw two of them, liquid. And the thing is, water autoionizes. It ionizes each other such that one acts as an acid and one molecule acts as the base. And I think we all can predict what happens. Acids donate protons, bases accept protons. Okay, so this water maybe accepted the proton from this, and we have, what is this again? The conjugate acid and the conjugate base. Well, the thing is, this is a reaction, and for this unit and for the previous unit, we've been learning how to figure out equilibrium constants. We should be able to write an equilibrium expression, Kc, for this reaction. So Kc, the concentration of H3O plus, times the concentration of OH minus, over, oh, my reactants are both liquids, so they do not belong in the equilibrium expression. So you can say over 1 or simply just don't write a denominator. Well, the thing is, this equilibrium expression has a special name if it's just water at equilibrium. That's called Kw. And Kw is the equilibrium constant of water autoionization. Constant of water autoionization. And that actually has a number. And that number is equal to 1.0 times, it's very small, 10 to the minus 14. And we know that equilibrium constants are dependent on temperature. This is the Kw at 25 degrees C. If we change the temperature, then we are going to change the Kw of water autoionization. All right, so don't be alarmed. We are learning a bunch of equilibrium expressions, Ka, Kb, Ksp. Here we're doing Kw, but it's all the same thing. If you could get an equation, you're just writing out the equilibrium expression, and we're just giving it a special name depending on what situation we are describing. Now, if you think about this, and we have these two multiplied by each other, two concentrations, and it equals that, let us put this into a box. This is an equation to remember. Kw simply is the hydronium concentration times the hydroxide concentration equals 1.0 times 10 to the minus 14. K's are unitless. Let's put this in a box. And this is always true with pure water. This is at 25 degrees C. And because it's equilibrium constant, this is at equilibrium. Once the reaction equilibrates, these concentrations are at equilibrium. So, what can we do with this equation? Well, we know that we could get pH from the hydronium concentration. So in a glass of water, what is that pH? that's a question that we could be able to answer. What is the pH in a pure? Okay, now pure doesn't mean only water molecules. I mean pure meaning that there's no added acid or added base. What is the pH in a pure glass of water? And we have that to work with. Well, the thing is, if you just have water and you make a molecule of H3O plus, you make the same amount of OH minus. So the molarities are identical. Well, if the molarities are identical, then all you're doing is solving for this. 1.0 times 10 to the minus 14 equals x squared, because they are identical. Therefore, x equals, and it's going to be a concentration, and looking for my calculator. Let me do this in my head. And it's a molarity. And what is that? That is literally the concentration of hydronium and the concentration of hydroxide at room temperature water. Well, okay, now that we know these two, that concentration is the hydronium, we know the equation pH equals negative log of the concentration of H3O plus, and therefore pH equals negative log of that number. Now, if you go ahead and do those calculations, 1 times 10 to the minus 7, and then we take the log of that, and we take the minus of that. So we multiply by negative 1, it's 7. Oh, you don't see that. It's 7. Does that sound familiar? That's neutral. So at pH 7, we are literally saying that concentration of H3O plus equals the concentration of OH minus, again at 25 degrees C. So that begs the question, well, what happens if we're not at 25 degrees C? That is part B. Let's take that glass of water that we had at 25 degrees C at the beginning, and let's put it into a hotter room. Let's go to 40 degrees. How about at 40 degrees C? Because K is temperature dependent, that number right there should be changing. I looked it up, and the KW at 40 degrees KW equals, let me find it real quick, 2.9 times 10 to the minus 14. Okay? So what is the question? The question is, at this temperature, what pH is considered neutral? What pH are we at for these two to be equal to each other? That's what neutrality means. Let me start a new page. Let's do this calculation together, or you could do it on your own. Remember, that's the question right there. Well, we know that with pure water, Kw equals the concentration of H3O plus times concentration of OH minus at neutral, concentration of H3O plus equals the concentration of OH minus. Okay. And therefore, we at this 40 degrees Celsius, we have a new Kw, 2.9 times 10 to the minus 14 equals x squared. Again, realizing that in our equation, every time we make one hydronium ion, we get one OH minus hydroxide. Now, that's going to be thrown way off if we start adding acid or base, right? We will not get a 1-to-1 ratio. But anyway, we're still with pure water, so it is a 1-to-1 ratio. And in this case, X equals, I did these calculations beforehand, 1.70 times 10 to the minus 7 molarity. That's equal to, again, the concentration of hydronium. And therefore, the pH equals negative log of 1.70 times 10 to the minus 7. And I also did this ahead of time, 6.77. Very interesting. In a hot lab, if you want your solution to be neutral, you are aiming for a pH of 6.77, and that is at 40 degrees, H3O plus concentration is now equal to the OH minus concentration. It looks like, okay, again, just remember that I looked up this number, okay, from a table, but it looks like as we raise the temperature, right, as we raise the temperature, the pH drops for neutral. Neutral pH drops. You want to memorize that? No, not especially, but it's interesting to know that trend. As you raise temp, the pH for neutral goes down. Does that mean that it is acidic? No, it means that it's neutral, okay? It would be acidic if the temperature was 25 degrees C and we got a pH of 6.77, but now we redefined neutrality for it to be 6.77. So something like 6.9 at 40 degrees Celsius would be considered basic. So let me write that down. We'll call this C. Very simply, it's just a couple trends. Let's say that if your concentration of H3O plus equals the concentration of OH minus, regardless of what temperature you're at, okay, that is a neutral solution. I didn't give this a title. That's okay. And then if H3O plus is greater than OH minus, that equals acidic. Okay, so you are going to see a lot of examples after we get out of this topic where they are not equal. And then if your hydroxide concentration is greater than your hydronium, then your solution is basic. Is that all I want to say? Give me 1 second while I look at my notes. Okay, good. That's it for KW. We are going to be using it in a couple of videos from now, but I think next we are going to talk about these other equilibrium constants, Ka and Kb. Ksp actually is towards the end. So let's tackle these two in the next video.